flexed on, y'all
You got flexed on?
go home. And then we came back, and I'm like, okay, you ready to take this? And none of us have looked at an ACT book.
When did this happen?
October 6th.
This year?
Yeah, that's when we took it.
That's when we took it.
And you got flexed on?
Yeah, because we studied all last year.
That was this year.
Yes.
I know, I grew up
We had to
on
make
this.
it up.
Yeah, because we didn't
Yeah.
There was a day where all the seniors took ACT.
Yes.
Whoa.
You sure about that? Just don't believe
I
it.
was there.
I'm sorry, I don't believe you.
Testify.
Can you give that to Taylor, please?
I can tell you. Alex did the Hunger Games.
Dude, I wish I could believe you, but I just don't.
He went the.
Sorry. What's up?
You don't remember a game class, in this class, when there was only 3 people?
I don't think that happened. Don't gaslight me, Aiden.
I remember that day you sent me home because I blew my nose. And then I got yelled at by O'Brien at practice when I finally got back because I hadn't touched my boots in 2 weeks. So it's all your fault.
I'm sorry. I was just trying to adhere to the school's policy.
Well, I need to blame someone. I'm not responsible for my own actions.
I remember that. I felt bad. I didn't know they were gonna like suspend you or whatever. That's just what they told. That's what we were supposed to do. Is people were supposed to go to the nurse thing.
Exactly, like a little micro pulp.
Lindsay's gone still. Kate's here. Attendance, the best time of the day, right, Trenton?
Is he ASVAB today?
Yes.
Is that for sophomores?
Yeah.
ASVAB? Okie dokie. We're gonna do number 10 because that one is
A big boy.
actually we'll do 9 first. 9, 10.
That is the word. That was the book.
There's also the word read and vote.
9, 10.
Big fat.
Thank you.
So-
Good. We're on point. We're on point. We're on point. Okay, so let's suppose you were a solid sphere was rolling along, just rolling along. Okay. Solid sphere. This is number 9. So the question is just how much total kinetic energy does a rolling object have? Okay. So this question, I hope, will remind you a bit of number 4, astronaut Bob. Remember when he threw that ball, and there was 2 sources of energy there. There was the rotation, and there was also the fact that the ball was moving, right? Makes sense. So this is the same kind of question, except there's one difference. Does anyone know what's the difference between a rolling ball and a ball that's just, a thrown bowling ball? Yes, Colin?
Is it because it's not? Wait. Okay, never mind.
Okay, it's fine.
Yeah, because it's like going at a constant velocity. It's kind of predictable. It's not like sliding or anything.
That's really close, I think. Yeah, there's the fact that it's rolling means that the velocity can be related to rotation. Because if you just throw a ball, there's no way of, unless you're being told, right? If you throw a ball, the ball could be spinning really fast or it could be spinning really slow. You don't really know unless you're told. But if a ball is rolling and not slipping, like you said, then there's actually a really nice connection between the velocity and the rotational rate, right? Okay, so that's the big difference, is that in this case, we're actually gonna be able to lump, by connecting those, mathematically, we'll be able to lump this all into one nice expression. So the total kinetic energy is gonna be, there's gonna be the energy from the movement, so 1/2 mv squared. And there's also the energy from the rotation, 1/2 I omega squared.
Sounds about right.
Okay. Sounds about right. So now the trick is we're going to go, well, we might as well do it early because then I'll show you on 10. This is exactly what we're going to do on 10. We're going to say, well, first of all, what's the I value for
2/5.
a solid sphere? It's 2/5 mr squared. And then this omega I can replace with, the omega with?
E divided by R.
V divided by R. So now let's plug in, now do we have all the numbers now? We have, so then what's cool about this is, do you notice how it's all in terms of just M, R, and V. I don't need the I, well, I's in there, but I don't need omega.
Let's see.
So, oh, one last thing. Let's not quite plug the numbers in yet, because couldn't I simplify this?
Yeah.
This will also give us some interesting information. So what's half of 2/5? 1/5. And then M, and then you've got R squared times V squared over R squared, which so amazingly, the R squareds are just going to cancel out. That's nice, right? So this is worth looking at. Who is contributing the most to the energy? Just the movement, the linear movement's actually contributing the most. Let's get a percentage there. I'll just on the side here. So he's contributing 1/2, right? Out of the total is 1/2 plus 1/5. That makes sense what I'm talking about? But I want to know what percentage of the energy belongs to the linear movement, and this one might be Mr. Quackmulator. I know we don't really need one, but I'm just being lazy. 1/2 divided by 0.5 plus 7. So 71.4%. So in this particular case, now of course that depends on this, right? Okay, so we can plug the numbers in now. So we have 1/2, the mass of the ball was 30. So 1/2 times 30 times the velocity was 5 plus 1/5. This part's, I think, pretty surprising. What didn't actually matter? Radius. Now, don't make the wrong conclusion there, because the radius didn't matter for this problem because we were given the velocity, right? I don't know why I read it like that, but if they'd given us like the rotational rate or something, or the rotational period, then you'd see the radius would have a big effect. But then the reason for this is like, you're like, well, it's like, how come the radius didn't matter? Well, if this number's big, or actually, sorry, what I meant to say is for a given velocity, if the radius is big, right? If the radius is big, then that's going to increase this number, but it's going to decrease that number. So the two effects. Canceling over canceling. So what do we get? What here? What is this? The total is what? So you guys agree with that? Yep. Joules. 525 joules. That's nice. Do we like? We understand?
Yes.
Are there any questions? No question? It's Wednesday today. That means we're all done at 8:49. Isn't that nice? Oh yeah, oh yeah, oh yeah. Does Griffin know that one? Oh yeah, oh yeah, oh yeah. Did I say it right, or is it Ayo, Ayo, Ayo? How did it go?
What?
It's from a memes. Oh, it's from meme stuff. What was it? What was the correct quotation? Oh Oya, oya, oya.
Yeah.
Oya, oya, oya. Maybe Griffin, like and comment and hit that notification bell if you understand the memes of oya, oya, oya.
Mr. Hall, during quick period yesterday, we can hear you super well, Mr. Coleman.
Oh, yeah.
Yeah.
Hear what?
You're going,
I think.
and then we started banging on the wall.
Well, I was making some shishas, and then the computer was making some shishas.
Oh.
Because we watched a whole bunch of sheesh.
That
Well,
was
that was Lakaya that smoked the wall. Did you
Yeah.
hear that?
And then we played a song for you.
Oh, we didn't hear this.
Oh, really?
Yeah.
What song did you play for them?
Interesting. Well, that's interesting. It was Foot Fungus by Ski Mask the Slump God, which is, in my opinion, the spiritual successor to Stinkfoot by Frank Zappa. About a guy who's wearing python boots. They were too tight. And he had to wear them to bed, and they got very stinky. Anyway. Interesting, though. The sheesh made it through the wall, but the
Very clearly.
foot fungus didn't make it through.
No.
Which is weird because a lot of times lower frequencies can transmit better through walls than high frequencies. And you think the sheesh is like a high frequency. So.
I mean, like, we could hear, like the sheesh, we could hear clearly of, like, what it was. But then, like, I remember hearing noise afterwards, but I don't remember being like, oh, that's a song or something.
Sheesh! Man, talk about memes are back. Sheesh has revitalized the meme sphere, I think. You know, ever since Big Chungus, nothing has come close. But now we're back. Right, Julia?
Maybe we'll make a whole loop.
Does Ben go around the house making some sheeshes? He doesn't. What? Not Ben?
He's probably not with the meme.
He's not with it. I thought Ben would be sheeshing it up. Okay.
We need to.
So, what we're gonna do here is for number 10. We're gonna use this result. Kind of over and over again. Because if you look forward, we're going to be talking about what happens if you roll a ball up a ramp. We've done the frictionless block sliding up the ramp, right? And then now we're going to say, well, a rolling object is just slightly more complex than that. So it's just, the math's just a little bit more involved. But once you know the kinetic energy of a rolling object, then you can just use that result, right? So, okay, hollow cylinder. This one has a beautiful result, if I remember correctly. Yeah, hollow cylinder. It's lovely. Because, so hollow cylinder. What's the I value for hollow cylinder?
MR squared.
No, yeah, MR squared. 1 MR squared, right? So the total kinetic energy, if he's roly-polyin, if he's rolling along, would be 1/2 m. What am I doing? What? Just, oh man. 1/2 mv squared, that's from the movement, plus 1/2 I omega squared, right?
Yep.
So his I value is mr squared, and his omega, that makes sense? Same thing as before. So the setup, maybe above the question, and it might be good to remind yourself that the K value for a rolling object would be 1/2 mv squared plus 1/2, or I shouldn't say rolling object, any object, really, that's its total kinetic energy. The energy from moving and the energy from spinning, right? Then if you know that V equals omega r, because if it's rolling, you can do this. And then if you know the shape of the object, you can do this. Right, Kate? Oh yeah, oh yeah. Okay. Now, what? Look at that. Look. Behold.
Oh, just MV squared.
Yeah. Right? Because you have 1/2 mv squared plus 1/2 mv squared. That's a whole mv squared. Look at that. That's beautiful.
Very nice.
Tears of joy. Yes, crying tears of joy. Applause abounds. Thank you, Aiden. Solid cylinder. You guys can finish these, right? We'll do one more together, then you guys can finish these. A solid cylinder is 1/2 mR squared for its I value. Okay, and so his calculation would be 1/2 mv squared plus 1/2. Be careful. So his 1/2 I omega squared would be. I said be careful, then I was not. I triggered. Okay. His I value is 1/2 mR squared, and his omega is v over r. Okay. So when all gets cancely-wancely, what are we going to have here? I'll show the intermediate step. Just
It's a 4, it's a plus 1/2.
so. I don't think you have to show this intermediate step, but you can if it helps you make sense of it. Certainly nothing wrong with showing an extra step, but half of a banana plus a quarter of a banana makes 3/4 of a banana. So as you can see, guys, I hope you can see it. What number is determining like how big this? They're all going to be MV squareds, right? What number is determining the size of this number?
The fraction in the I value.
That coefficient in the I value. So like, now it's not obvious, how does a half turn into 3/4? For the hollow sphere, what's this number on a hollow sphere? 2/3, and a solid sphere is 2/5. So just go ahead and finish those. And then we'll check our answers. And from there, I hope it makes sense how you're gonna complete 10, and then also 11 is the same thing. It's just asking us to generalize that result using the number k there, and you'll have like a general formula that you could then any object whose I value can be written as a coefficient times mR squared, you then have the rolling energy for that thing. So, yay! Oh yeah.